Just a few slides, but most of today would be a demonstration of what you can do with the services that were developed through the iMagine project. From the get-go, I would say that this was a joint endeavor between the laboratory and Photonower, which is a private company specialized in computer vision. So they do a lot of things, and they helped us on this. An overview of our actions within iMagine. Our goal was to modernize the ZooProcess processing pipeline. The ZooScan images processing pipeline, which is ZooProcess, and to apply it to a long time series. And so the idea is that we would keep the general principle of the process, which I guess a lot of you know. That's why you're here. So you start by filling the metadata, but what we will do more is we'll try to match the metadata to some known term in some international vocabularies. Then you acquire your scan, you process the scan image, and this, instead of being in ImageJ macros, will be done in Python for speed. And then the big new thing was that we will try to help the users in the separation of multiple organisms. You have a few examples here. What you currently have to do is go back manually and draw some white lines around these organisms to extract them. And so that will be the focus of today. There's 2 AI-based modules to help with this. Then there's some quality control. And finally, you upload your files to Ecotaxa, currently manually. So why did we focus on this step of separation? Well, we did some timing. And over an average of many scans, what we see is that per vignette, per image of multiple organism, it takes about 3 seconds per image to detect it. You go through all the images and you sort them, and about 11 seconds to draw the lines. Of course, some images take much longer, others take a shorter time, but that's an average. But if you count that on average, again, you have about 100 such images per regular sized scan. That means that in total, it takes you about 20 something minutes per sample. And we count that, all in all, with the scanning and the classification, etc., you can go to 4 samples per day. That means that people are wasting 1.5 hours of their life just dealing with the multiple. So that seemed like a good target. So the current pipeline is what you have on top. You scan, you go through ImageJ that generates a file and a TSV file and some images, and manually you upload this to Ecotaxa. The goal is to replace completely all this with what you have at the bottom, which is a set of interconnected applications that would be in a client-server architecture, so you can have your images and all the processing happening separately from the machine that you connect to the ZooScan. But it can also be all on the same machine, of course. And so you see it's a combination of different blocks written in different languages. I won't talk about this too much today because unfortunately that's not completely ready yet. But that's the final goal. What I will speak about is these 2 orange boxes, which are 2 AI-based tools. One to automatically classify the images of multiple organisms, to extract them faster, and then one to automatically separate them, so draw the white lines. Okay. The idea is that these AI blocks, they can run locally or they can run in the cloud if you don't have the resources to run them locally. And this is something that we'll see today. So briefly, a few words about how this is done and some performance metrics. So the classifier, it's a network architecture called MobileNet, which is a small architecture, which we found was good enough and actually very good for plankton images. It was trained on ImageNet, which is images of cats, dogs, tables, etc. from the internet, but we specifically retrained it on a data set with 16,000 single objects from a variety of groups, from a variety of places, and 7,000 multiple objects. So quite a lot so that the network learns to recognize those specifically. And what we see is, so it's just a classifier, multiple, not multiple, okay? And what we see is that we have a recall of 90% of the multiples. so which is good, but which also means that we're missing a few. And among those that the network identify as multiple, 80% are actually multiples. Okay. So the idea that you would run this, you extract all the multiples, and then you run them through the separator. So the separator is using a different architecture, which is based on what's called panoptic segmentation. Panoptic segmentation means that we're segmenting the whole image, okay? And we're using, a way to do this model that's called mask-to-former to do this. So that's a deep learning approach to segmentation, which works intelligently to separate objects, but which does not work at the pixel level at the boundary of the object. And it's really important to have the pixel level masks so that what we do now is backward compatible to the way that ZooProcess has done it for the past, probably 10-something years. So we use those deep masks to identify the object, and then we use something that's called a watershed algorithm. So we just grow a region as the water would flow on a topography, let's say, to really match the objects to the pixel, so that it's directly, and it's really completely compatible with what was done before. So in terms of performance, what we see is that when we run this on images of multiple and single objects, in 73% of the time we get the appropriate number of objects. So sorry, what we did was take some images of multiple objects and then have them separated by a human, and that's our ground truth. And what we see is that in 73% of the time, the automated way matches the ground truth. So there's the correct number of objects, and the objects are well placed. And another good result that we're happy with is that when you run an image of a single plankton through this, most of the time it keeps it as a single plankton. It only 2.5% of the time will it cut it, so it will be over-segmented. Okay, so overall, it's not perfect, but I don't think any AI-based solution can be perfect. But we were really happy with the results. And what that means is that it will require a manual verification step to get to 100%. And this is what will be integrated in the new version of ZooProcess. There will be a user interface to look at the images and correct them if it's wrong. So a few examples currently absolutely not corrected. This is the raw output of the fully automated procedure. And so what you can see is that it draws lines to separate pretty well, I think, in many cases, the different objects that are on the images. So I think I have a few examples like this. So this would cut that part. This would correctly separate these two copepods. In that case, which is a bit more difficult, it actually does a pretty good job of cutting out the two copepods. Of course, it's not perfect. For example, here, what you see that it cuts the two antennae of that copepod, which is wrong. Here, it cuts this appendicular. So this is a typical example of over-segmentation. So it cuts where it should not cut. And here, it decides to cut here when really a human would have cut there. So that's what I was saying. It's not perfect, but the idea is that it would be an interactive solution where the system would propose stuff and speed up the work of the human operators, and the human operators will only have to correct rather than do everything manually. Okay, so let's go on for the demo. As I said, this at some point, ZooProcess will be replaced by something that integrates this. We hope that this will be soon, but currently that's not the case. But the AI tools are there, and you can use them now. Everything that I'm going to show you is in this GitHub repository. You have the URL here and the QR code that would lead you to this. Okay, so let me exit that and start with this. Okay, so this is the GitHub repo. You see that there's a numbered file. So this is a progression towards more and more complicated applications. Okay, and so the first thing is that through the imaging project, these AI modules are actually hosted for you. Okay, so you can click to, go to a URL, which is Inference Welton, which is one of the federated infrastructures through the imaging project, and you have access to the model, okay? So let me just open that in a new window. Okay, and so to quickly check that it works, so this is a presentation of the API of these modules. So these modules offer an API, meaning a way to call them programmatically, okay? And this is a documentation of that API. So for example, there's an endpoint, so a function of this API that is just giving you metadata about the model, okay? No, sorry, that's this one. And actually from this web page, you can try it. So I say, try it out, execute, and then it runs, okay? And then I get the result, which is in that case, a simple description of the service. What will be more interesting for us is that there's one endpoint that we'll be using, which is a predict endpoint. So send something to the model, get the prediction. So in that case, I say, try it out, okay? And there's two inputs. The image that I want to process. So currently I'm looking at the classifier, so the image that I want to classify. And then there's a second option, which is to crop a certain number of pixels from the bottom, because if you use regular images produced by ZooProcess, you have the scale bar at the bottom. So I can choose a file, okay, and then okay, and then I have a few images. So there's a few example images in the repository also. The S1s are images of single object. The M1 are images of multiple objects. So let's try this one, for example. Okay, those files have a scale bar at the bottom. Actually, I can show some of them. Okay, so they are the regular vignettes that you would get from ZooProcess. Okay, so they have a scale bar, and that scale bar is 31 pixels, and that's the default to cut. Okay, and then when I click execute, what happens is that this image is sent to the server in the Welton infrastructure, which is somewhere in Ireland, and I get the result. The result is this, the name of the image that I uploaded, and the score. The score is, in that case, the probability for this object to be a multiple object. It was a multiple object, okay? It was the 2, 8, blah, blah, blah. So it's this one, okay? And you see that the classifier identifies it as a multiple with a really high confidence, so that works. We can also try with a single, okay? And you see that in that case, the score is very low, so it has a very low probability of being a multiple, so it's probably a single. So happy, it works, okay? What I want to show you also is, okay, that you can upload one image per image, okay? But you can also upload a zip file containing images. So in that case, it's a zip file containing all the other images, and I execute. And in that case, it processed 14 files. I get all the names of the files, and then I get all the corresponding scores, okay? And we can quickly check that, many of them are multiple and they have a high score, so that works. And some are, really low scores here, and they correspond to the single. So on these few examples, it seems to work quite well, okay? Of course, there's the same for, oh, sorry, I should open it in a new window. There's the same for the separator, okay? So that was the classifier first and then the separator. So we can also try it. I'm going to try it with a single file. Okay, let's use the same as before. Okay, and then there's two choices. So there's the same one as before. So how many pixels you crop from the bottom. And then the separator, it starts by trying to identify which portions of the image are separate objects. And so it proposes masks, and there's a threshold of the probability of these masks being correct. The lower you put it, the more different masks it would accept. The higher you put it, the more stringent it is to make sure that it identifies something it's really confident about. The default is 0.9 because we we'd rather be confident than having, extra lines everywhere, okay? But you could experiment with it. And then I execute it. In that case, it's a much larger model, so it'll be much longer to run. I mean, a bit longer. It's a few seconds, basically. Because so it's a much larger AI model, but also then there's some post-processing to get to draw the separation line. So that's why it takes a bit of time. And then you see the answer here. So the answer is status okay. Prediction, it's a list of predictions because you can, same as before, upload one or several images. And then you have the name. You have an element which is separation coordinates, which are all the coordinates on the image at which you should draw a white line to separate the objects. You have the size, the original size of the image, and you have an overall score, which is a mix of stuff, which is an index of the confidence of the model in the separation it made. It's far from perfect, but it gives you an idea of how much you should check what the model did or not, basically. Okay, so what you see is that starting right now with just a web browser, you can use these two modules by just clicking around, okay? Of course, when you use the ZooScan, it doesn't produce just one image, it produces many, so you don't want to be uploading many images this way. There's the zip file solution, which you can already upload quite a lot that way, but probably you want to access all of that programmatically, okay? So from this interface, what you see here is that you have a curl command that would do exactly what we did by clicking around, but that you can just execute in a shell. So this is the second step that I have here, okay? So to classify an image, I can go to the classifier, okay? I can copy this, paste it, and then execute it in a terminal, okay? So in that case, I would execute that in the terminal, okay, run this, and then I get the result, which is just as before, name of the image, score. It was a single image in that case, the score is low, it still works, okay? Actually, so you see that the curl command here is very explicit about a lot of the metadata, so the headers and everything. Actually, you can even make it simpler and it still works, okay? Get the same result. Because it's a command, you can script it. So this is a bash script, a shell script, and I can do a loop on the images, and I can send the command for each individual image, and you can see the result. So for each time, it sends the image online to Welton, gets the result, and prints it, okay? And then I've just run the 14 images this way. Again, you can create the zip file, okay? So what I'm doing here is that I'm creating this images.zip, okay? A few pointers about the options. The -J option is so that all the images are put at the root of the zip file. This is necessary because they will be unzipped online and we can't go into directories. So all the images need to be together at the root of the zip file. So you can fetch images from many places. If you put -J, it will just all, bunch them all in at the root. X is we don't want extended file attributes, we don't care. And 0 is that I don't even try to compress them. The ZooProcess vignettes are JPEG already, so they are already compressed, so there's no point in trying to compress them more, okay? So I have my images.zip, and then I can upload the zip file. Instead of calling the API with a JPEG file, I can call it with the zip file. The only thing that I'm changing is the name of the file, of course, and the type of the file. Previously, it was type JPEG or nothing, and it was guessing correctly. If I use a zip file, I need to explicitly set it. So I can run this, then this will upload the zip file, uncompress, process, and give me back the result. And in that case, again, I have my vector of image names and my vector of probabilities, okay? And for the separator, it's the same, and I won't do it now because, again, it's a bit longer. So that's one way to automate it through shell scripts. If you use, again, ZooScan data, you're probably used to coding in some languages. So You can do exactly what we do with curl first you can use your language to generate the curl command. That's one way to do it. Or you can use specific packages, and I'm going to show how to do this with both R and Python. So in R, the package of interest is called HTTR2, which is a package that allows you to make web requests, which is the way that this API works. Okay, so the first thing I would do is start R and list my images. Oops. Okay, so I have the path to all the images. And then I will construct a request. So it's really equivalent to constructing that curl command that we saw before. So I give the URL, I give the parameter, which is I want, bottom crop to be 31. I give the type of request. So the type of request, you can see it from there. It's a post request, okay? And then I give what I want to upload, which is in that case, just one image, the first one. And then I perform the request, okay? So let's do this. I get the request. Now it's a request object, okay? And if I want to extract its contents, the answer of that request is in a format called JSON. I want to convert that into something that I can work with in R, which is that next command. And in R, it converts the JSON object into a list, an R list, with one name and one score, the name of the images that I just uploaded and the score. Same as before, I can zip my files. See, I'm using exactly the same options as in the zip command before, so that I ensure that all the images are at the root of the zip file. And then I can do the request, and instead of sending just one image, like here, I send the zip file, and I explicitly tell it that it's a zip file, okay? So I do the request, it uploads the zip file, gets the results, and again, I can extract this into an R-compatible format, which is again a list with a vector of names and a vector of scores. For the separator, exactly same as before, except there would be two parameters. Again, I can do it with one image. Again, it's going to be a bit longer. So let's wait for this to finish. Okay, then I will extract, again, I get a JSON response. You remember the object was a bit more complicated. There was, the name, but there were also a vector with the object coordinate, the coordinates of the white line, etc. So the command to extract this into an R-compatible format is a bit more complicated, but this is what we get in the end. We get status, then prediction, that's a list, because I can send many images through a zip, so there can be several of these lists. And then I get the name, the coordinates in X and Y where I should draw the white lines, the size of the image, and the overall confidence in, how good were those lines. And it seems to be very confident. So what I can do from this is just extract the prediction part, okay? The status, I saw it was okay. And then just to show you, I can read the JPEG image, okay? And then, so I could then plot this image, okay, this is there. And so I would want, of course, it to separate the copper plot from that long thingy here. So what I do here is that I get the separation coordinates. Important, I add one because R is 1 based for the indexing, while Python is 0 based and everything runs in Python before. So to get the correct things shifted by 1 pixel, I need to add this one. And then what I'm doing here is that I'm resetting the colors. It's RGB, so I'm setting those pixels that should be the separation line to be all red, okay, so that we see them correctly. And this is the result. So these separation coordinates, okay, these numbers correspond to the numbers of those pixels, and you see that this is where the system would draw the line. So here I made it red. What I would do in a regular situation is that I would make it white and then rerun this so that, separate these two things and remerge them so that they appear as two separate objects, okay? So I can do it with a few images because prediction is pretty long and there's a timeout. You can't send 1,000 images at once, okay? On Walton, at least, you need to send them few by few, okay? Here, what I'm doing is that I'm just defining a function that does what I did before. So send one image, get the response, or send many image through a zip and get the response, just so that I can time this, okay? So now what I'm doing now is sending 14 individual images to be classified, okay? And measuring the time it takes, and it took 6-something seconds, which is longer than in my tests, okay? So maybe some of you are actually sending stuff to the infrastructure at the same time. And here what I'm doing is that I'm sending the same 14 images as a zip file. And you see that it was faster, 2 times faster. Actually, when I tested it when the thing was free, was more 3 seconds and less than 1 second. So it's there's an overhead in sending one image, getting the answer, sending another image, getting the answer. So you have the zip solution that gets rid of this overhead, okay? Okay, and I can test separation on a few images and show you the result. But again, because this is a bit long, I will probably skip it. But you have the code. The idea is that you can then take that code and run it yourself. I see stuff in the chat. Okay, no, that's not for me. Not for now. Okay. So this was for the ones of you who use R, but some of you, unfortunately, use Python. But I'm next with you too. And this is how to do exactly the same thing with Python, okay? So I'm still in RStudio, but I'm going to fire up a Python interpreter. And first thing first, as before, I'm going to list all my images, okay? Then the package in Python that allows you to do web requests is called requests, okay? That's the HTTR2 equivalent, let's say. And here it's just a small function to define the URL to go to Walton. So it's the same URL, except it's either classifier or separator here. So if I call it with classifier, I get the correct URL. Okay, so this would be this full URL. Okay, and then same as before, I have some parameters to set, bottom crop 31, and then the files I want to upload. And in that case, I need to open an image explicitly and then send the corresponding bytes. So this sends the request, gets the answer, same as before. The answer is a JSON file. I want to convert that into something that is a Python object that I can use. And this is done with r.json, okay? And this is now a Python dictionary with the name of the image and the score of, the probability of this image being a multiple, okay? So we can check this is actually a dictionary. Same as before, you can zip things. So it's not just one line, it's a bit more complicated in that case. You create a zip file and then you put the images one after the other in the zip file. That's still very fast, okay? It's done. And then I can post this zip file to the API. Same thing as before. The files here is a bit more complicated. In that case, I just gave the JPEG image, okay? Here I need to give a name, then the content, and then specify explicitly that it's a zip file so that it's recognized correctly on the other end, okay? Then I'm sending the zip file with the 14 images, getting the answer, and then translating the answer in a Python dictionary. And again, you get your list of images and your list of scores, okay? Separator, exactly the same as before. You have 2 parameters, and you can send 1 image. Okay, let's wait a bit. I'm guessing that this is long because some of you are using it. Okay, so same structure as before. We get the separation coordinate, etc. I can do what I did in R, meaning that I'm reading the image and then setting the color to be red for the separation line and plotting the image. Okay, and this is what you have. Of course, you have exactly the same result because it's calling exactly the same code. Okay. one thing new that I'm adding in this Python script is that, as I told you, then you can draw a white line here and then remeasure this, like take this part out and take this part out and measure them as two separate objects, okay? Which is what you want to do science with afterwards. So to do this, I'm going to use the image processing package scikit-image. Okay, so I'm sending one image to be separated. That's actually probably that one. Could have saved that comment. Okay. Okay, I got the answer. Then I'm reading this image and plotting that image. Yes, so that's the same as before, okay, without the white line. So now what I'm doing here is that I'm extracting the separation coordinates, and at this separation coordinate, I'm putting a 1 because it's a grayscale image. So putting 1 means putting white. And if I do this, then you see that, hopefully you see that now there's a white line separating these two objects, which is exactly what you would have done manually by drawing a white line in ZooProcess, okay? So then I can take that image, I can remove the scale bar, okay? So now I have only these two objects. Then I'm here, what I'm doing is that I'm basically redoing what ZooProcess does internally, meaning thresholding the image and then measuring each object separately. So this is the thresholding, okay? So I should have two objects. You see that I have a lot of small dots. The small dots are due to the JPEG compression, so they're artifacts. What I'm really interested in is measuring these two big blobs. So I've thresholded, then there's a second step, which is labeling, so assigning a number to all these separate blocks of pixels, okay? Then I'm measuring region properties. So this will measure the area, the field area, the equivalent spherical diameter, the major and minor axis, etc. So things that are really similar to what ZooProcess usually gives you. Just in that case, it's computed by scikit-image and not by ImageJ. So they are not numerically exactly equivalent, but they have the same meaning, okay? Then I can extract those properties as a big table, okay? And you see that in area, I have some big ones and some very small ones. The very small ones are all the artifacts. So I'm going to cut out all the artifacts and I'm left with two objects, okay? That was the copypod and the long thing. And I have their area fields, blah, 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 their major, minor axis, etc. And so I can do science with these values the same way that I would do science with the values that are output by ZooProcess. Of course, when all this is included in ZooProcess, the measurement would be exactly the same as before. Okay, so this is it with the Python stuff. And I'm running probably out of time. So I'm gonna do this quickly. So you see that all of this, okay, yeah, no, I thought I was frozen. No. So all of this I did without installing anything because it all runs in the cloud on the well-turned service that is provided by iMagine. You also see that it can be a bit slow because it's running on CPU and there might be several people using it at the same time. If you have a lot of images to process, you can install this on your computer or your infrastructure, okay? So this is all detailed here. I won't do the installation live because it's not useful, okay? But it's quite simple. It's all Python, so you need to create an environment to isolate yourself. Then you, from the rest of your Python installation, you get the code from GitHub. You install everything. You get the weights, so the model configuration from GitHub also, and then you run it, okay? So if I do this, so I've done the installation already. So I do conda activate my environment, which is called ZooProcess multiple. Okay, so it's activated. And then if I do, let's do this. Okay, so now it's running, but it's running on my computer on that port. Okay, so let me go back to RStudio. So in R or in Python, instead of putting the URL of Walton here, I will put the URL of my own computer. Okay, and let's try. Okay, and I get the same result as before. Okay, and let's do this, and then the pass run. And I'm going to run two models, the classifier on port 5000 and the separator on port 5001. So it starts, and then it's ready to receive requests. Okay, and so now I can do this. And the separation, instead of being done on Walton, is done on my computer. And you see that it was marginally, I mean, it was still a bit faster, okay, because you don't have the overhead of sending the data back and forth. And it's my computer, so I'm the only one using it. That said, my computer, it's a small laptop. It doesn't have a GPU. But of course, you can install this somewhere with a GPU, okay? And, well, actually, what I can do is just change this. So I have installed it on a server here, and it's running, yes, it's running on that same port. And this server has a GPU, and you see that it was quite a lot faster than it was on my own computer, okay? So the installation, again, it's just two times the same thing. One thing that I would say that the dependencies of the classifier and the separator are very similar. So that means that you can have only a single Python environment and you can run both from that Python environment, which makes your life a bit easier, okay? If you want your life to be even easier, all the iMagine modules are distributed as Docker containers, Docker images, okay? So you can install, you start by installing Docker. Yes, it's there, okay? And then you go on Docker Hub and you search for AI for OS Hub and ZooProcess, and it will come up with, so all the AI for OS Hub are, I mean, many of those come from iMagine actually. But then the ZooProcess one, there's two, the classifier and the separator, okay? And then from this, you can pull that image and install it on your computer. And you don't have to worry about Python environment and dependencies, et cetera, et cetera. You just, pull and it's available. Once it's pulled, you run it, okay? And when you run it, you need to set one thing, which is, remember when I installed it, it was running on port 5000. For those who know Docker, Docker is like having a separate computer inside your computer. So the port 5000 of that computer is only on that computer. To use it, you need to map it to a port on your computer. And so to not mess it up, you map it to a different port, so 50,000, for example. And you run, okay? Here you see exactly the same thing as when I did the local install. It's starting, etc. Now it's ready. And what that means is that I can call it, okay. From R, you see that I'm calling my own computer because Docker is running on my computer, but it could be running anywhere. I'm calling with the port 50,000, which is the one that I mapped to the port 5,000 inside the Docker. Okay, it's getting a bit more complicated. And of course, it's not working. Why is it not working? Oh, maybe because I have... oh, that's strange, because it received the request. So... okay, that's the point of live demos, is that at some point they fail. But it should work. Okay, maybe I have too many things running at once, so let me kill that. kill that. And in Docker, make sure that no, it should be. Okay, no, it doesn't want to. Believe me, it was working when I tested it. Okay, so overall, 3 solutions to run it. Either you run it online on the Welton cluster and you don't have anything to install, or that's the easiest. The second easiest is probably the Docker version. Also, although it doesn't work right now, I'm sorry, but normally in Docker desktop is just clicking a few things, waiting for the download to happen. But you don't again have to install anything because Docker packages all the dependencies for you. Okay, and the last one is installing it yourself, following these instructions. So installing the correct version of Python, the correct version of the packages. It's still not very difficult, okay, and it's going to take a few minutes, and then you have it running on your computer. If your computer has NVIDIA GPU, everything will be faster, okay? And the last thing that I want to show you is that currently what I've done is send a few images, send a few vignettes, get the separation from them, and then optionally in Python, I've showed you how you can extract measurements with Python that make sense, okay? But what you might want is to have exactly the same measurement as what ZooProcess does. So to do this, if you look at, this is a scan from ZooProcess, okay? So this is what you find in ZooProcess scan and then _work, okay? So this is one scan. You get your ecotaxa.tsv file, all the JPEG images, I mean the vignettes basically, and then at the end you have a log, measurements, a mask, and the actual image, etc., etc. In there, you can have here a file that's called blah 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 _sep. And these are the manual separation. So when you do the separation manually in ZooProcess, it creates that file. So the code that I'm showing you here recreates that file, but using the automated approach. So it's going to take the full image, it's going to crop every single object, is going to, exactly as ZooProcess would do, okay, because it's using the masks that ZooProcess uses, then it sends all these objects to be classified. It takes the classified ones, the ones classified as multiple, and sends them to the separator. It fetches the separation lines and then draws them on that sep file, okay? So I can hopefully try to run it quickly. So what I'm doing here is reading the scan image, reading the mask image. So that's all generated by ZooProcess, okay? Now here what I'm doing is that I'm cropping every single object, okay? And saving that as a mini vignette. So just the object, no scale bar, no nothing, okay? So in that scan, I think there's actually number of objects. There's 1,422, okay? So I'm going to make a zip file with this 1,422. That's done, okay? Then I'm going to send this to, yes. I'm going to send this to our local server, in that case, to do the classification on GPU, okay? And there it's done, okay? So what happened just now is that I sent, let's say, 1,500 files. It classified everything, and then I have in that object the 1,500 probabilities, okay? I can detect the ones that are multiples. In that case, I say everything that is above 40% chance of being a multiple, let's call it a multiple, okay? I create a new zip file with these objects, okay? I think there's 400 objects that are potentially multiples. Then I'm running these 400 objects through the separator. This will be a bit long, but hopefully not too long, okay? And then the final step, once this is done, so I'm seeing that it's running, but it's still 400 objects that need to go through everything, okay? And then what I'm doing here is pasting the separation line on this big mask that is the size of the scan. Then this, I could take it, put it back in my ZooProcess project and regenerate the vignettes with ZooProcess, and I would get a perfectly compatible. So it's done, okay? So that was 400. That's not too bad in terms of timing, okay? And then I've created the image and I saved the image, okay? It's there. So it has, oh no, it's there. So it has appeared here. Does it work? No, I don't think I can open it this way. Anyway, this is an object that is pure black and with some white squiggles, which are the separation line. And again, this I can put back into the project and let ZooProcess do the rest.